In this video, we will compute the linear regression equation for a set of data. I will be following example 1 from the linear regression section of chapter 12, linear regression and correlation. I've already entered the data from this example into my calculator, as you can see. If you haven't done so, if you were not following the scatter plot video, you could take a look at that or enter this data on your own now. The next step, in order to perform the linear regression, what we'll do is we press stat. Well, let me quit this though, and press stat, and then over to tests, and we go over to calc, and you'll notice a linreg choice there, and press enter, and then you need to tell it which lists you want. So it wants to choose list 1 and list 2. Press enter. And there is our linear regression equation. A is 4.827 and so on, and B is -173. And so the linear regression equation for this particular example is y is equal to 4.82739 times x minus 173.51. If we want to graph this equation, the most efficient way to do this is to press stat again, go over to tests now, and choose the linreg t-test. In this case, we're going to enter the lists that we entered before. So list 1 and list 2 are the two that we chose. Frequency is only there if you're entering your data as a frequency distribution. Otherwise, just leave this as 1. This next item is really for the linear regression hypothesis test. So generally, we're going to leave this as not equal to 0. What that is referring to is the correlation coefficient and the slope of the linear regression equation. Finally, there's a place for you to put a regression equation. This is handy for graphing your regression equation. And the way you do this is you press the vars key, choose yvars, oops, okay, sorry about that. Move over to yvars and choose function. And then notice that you have some choices here. You want to select one of the function variables that is currently empty. One way to check is to actually press the y equals key and see if, and then clear out all of your y variables if necessary. I know that all of mine are clear, and so I'm just going to choose y1. You may need to clear out y1 before you use it. Finally, go ahead and press calculate. And you get the regression equation along with a p-value. Now that p-value corresponds with the hypothesis test, and that is the hypothesis test that the slope of the regression line is not equal to 0. And so there is evidence to suggest that both the slope and the correlation coefficient for this problem are not equal to 0. You'll notice here they've switched A and B from the previous slide. Don't let that worry you too much. In this case, B is the slope and A is the y-intercept. But the important thing here is, well, there's the correlation coefficient, 0.663. There's also the coefficient of determination, 0.439. But the important thing is that because of the way we set this up, when you press the y equals button, you actually get the regression equation. So when you graph this, the regression equation will show up, and it cuts right through the middle of your data. While we're on this, let's go ahead and see if there are any outliers for this particular problem. Outliers are defined as points that fall outside of 2 standard deviations from the predicted value. We can figure out what the standard deviation is by going back to the, oops, I didn't mean to do that. There, going back here, and you'll find the standard deviation is listed as 16.412. This is a standard deviation for the regression equation. And so what I'll do to determine if there are outliers is I'm going to put 2 additional lines on my graph that are 2 standard deviations above and below the regression equation. This is actually quite easy to do. Just remember this number, 16.4, and then go to your y equals menu, and then go down to y2. What I'm going to do is I'm going to have y2 equal to, press your vars key, go over to yvars, function, and choose y1. So y2 is equal to y1 minus 2 times 16.4. I think I need to change this to a minus key. There, not a negative sign. Okay, so that's what it should look like. I'm going to do the same thing here with y3. y3 is going to equal the y1 variable plus, in this case, 2 times 16.4. Now when I graph this, I'm going to get 3 lines. The middle line is my regression line, and then the other 2 are kind of the bounds for outliers for this graph or this data set. So there's my regression line, there's the lower and then the upper. You can see that that upper line is actually below one of my points, and that point is considered an outlier. In order to be sure, though, that you are dealing with an outlier, press the trace button, and you can see that that particular point is x equals 65 and y equals 175. Now if you go down, press the down key. Let's see, not what I wanted to do. I wanted to go to the other equation. Okay, here's point 1. Go down, oh, I guess we're on the line. This is the line y1, so I have to go back on y1. This would be the predicted value of y for an x value of 65. Close enough, 65.02. So the predicted value of y would be 140. We would predict that someone who got a 65 on their test 3 would get a 140 on their final exam. Now let's go down again, and this, I'm off the screen here. That's the lower bound for this the outlier equations. There it is, the upper equation. In this case, y is equal to 173 is sort of the maximum acceptable non-outlier for this particular x value. And it turns out that my x value is 175. So 173 is the biggest that I would accept as a non-outlier. This is 175. So you can check to see if you've gone beyond the line, because sometimes the dots will be very close to the line. And so to check, you can use the trace function.